So my name is Paul Hudson, and when the SwiftGG people asked me to come along and speak here, I was very grateful. You know, I've done wonderful work in the past. I looked back and saw last year's event, and last year's event, of course, they had lots of incredible talks about graphics and Vision OS and all that kind of thing. So I thought, okay, what's the theme this year? This year, they're expanding. They want to do AI as well as graphics. Okay, cool, so AI and graphics. I'm thinking to myself, what kind of talk could I do that would include both graphics and AI at the same time? Now, when you say AI to a person in the street, chances are they think of ChatGPT. Something you can just talk to in a natural, human way and get a reasonable answer in natural language. But really, that's very new. AI has been around a lot longer than ChatGPT, always seeking to answer the question, how can we make a computer act like a human? Or more literally, how can we teach sand to think? And one of the oldest examples, of course, of AI is video games, where you could play against computer players at a range of difficulties. Now, for me, when I was younger, I loved to play games like Command & Conquer, or Age of Empires, or Civilization, these strategy games. And in the early days, they had AI. They had very simple AI that looked like this. Effectively, a bunch of if statements. If the player does one thing, the AI responds in a specific way. If the player does something else, the AI responds in a different way. And so on, and so on. This approach worked well to begin with because it allowed the AI to respond to specific player actions in a way that seemed logical, seemed clever. But it hit problems fairly quickly. Because what happens is, having simple, hard-coded rules built into your game meant that once players figured out what those rules were, the AI became predictable. Every time it did this exact action, the AI responds in the same way. The game becomes easy to win. So developers, we did what we do best. We added complexity. And that meant more and more and more if conditions to provide more variations, making the internal rules harder to figure out. Of course, that just meant it took longer for players to figure out, but it still happened eventually. Worse, all the extra complexity meant our AI started to have bugs. One of the most famous examples of this is a myth about Mahatma Gandhi. Now, there's a belief that in the earliest Civilization game, it had a bug with the character Gandhi. Gandhi, of course, was a famous world leader who believed in peace, peace everywhere. But in the game Civilization, people believed as he was starting out fairly peaceful, he had a level 3 aggression. As he became more peaceful, his aggression gets lower and lower and lower until it hits 0. And then they believed if Gandhi took any extra action to become even more peaceful, they couldn't go any lower in a single unsigned integer, and so buffer overflow happened, making him the most aggressive world leader imaginable and launching nuclear weapons at all his opponents. And the myth of nuclear Gandhi became so strong that it was actually added to a later version of the game as a real feature. And so developers have a problem. They were adding more and more rules to their games, along with bugs and unintentional behaviors that come with those rules. And with hundreds of thousands of players talking on the internet, even with lots of rules, it was only a matter of time until they could figure out how to beat the AI. And this is where developers came to a surprising conclusion. Rather than adding all sorts of increasingly complex rules to govern how the computer players should behave, they could actually replace large amounts of their if conditions with a random number generator. The AI would effectively roll a dice to decide what to do next. And so in games I liked, like Age of Empires, the AI might roll a 1, and that might mean attack from the front. It might roll a 2, which means attack from behind. Or a 3 might mean attack from the sides. Now, you might think, this sounds terrible. Before we had a complex and rich and clever set of rules, and now it was trivial. How could players possibly be satisfied with that? The amazing thing is, players loved it. In fact, what happened, from the player's perspective, we started to read behaviors into the randomness. We would say things like, oh no, the AI has seen a weakness on my left army, they're attacking me there. No, they just rolled a 1 internally. It's completely random, but we believed it was real. Effectively, we realized there was no need to spend a huge amount of time and money building increasingly complex systems, when really we could get the same result at a tiny fraction of the price. And this will sound very familiar to anyone in the AI space right now, where you can spend not a lot of money and get some great results. And this is the kind of AI I want to talk about today. AI that is fairly simple to implement, but still manage to work far better than you'd expect. In particular, I want to show you a technique called flocking, which is commonly used in computer graphics to create realistic groups of moving objects. If you watch a flock of birds, or swarms of fish, or any other group moving together, you'll see they exhibit all sorts of complex behaviors as they swarm around. For example, flocks like to stay together, but they don't want to be too close. They want a little bit of space. Flocks like to move in the same direction, but they can also change direction together at the same time. It's really complex behavior, how swarms behave, and remarkably beautiful to see in real life. And you might think creating such a thing requires some complex logic, but really, they exhibit just 3 fundamental patterns. First, cohesion. That means they adjust their position to stay roughly in the average position of all the other creatures in their flock. Second, separation. They don't come too close to others. They want to be close, but not crowded. And third, alignment. They constantly adjust their direction towards the average of all the other directions in the flock. Now, although these behaviors are simple individually, if you combine them together, you'll find they create something so beautiful, you'll almost think your objects were real. We're creating what looks like advanced artificial intelligence using simple logic. And this technique was first discussed by a man called Craig Reynolds in 1987. He called them boids. He describes the concept of bird-oid objects, or just boids. Now, the name comes from the idea, if you imagine a person with a very strong, stereotypical New York accent saying the word birds, they would say boids. That's where the name comes from. And we're going to implement it together ourselves here in Swift using SwiftUI for all our rendering. Now, I should say, there's a lot of code coming up. So if you're in the front row, prepare yourselves. To get started, we're going to create 2 classes that make our flocking behavior. We have a boid class that represents a single object in our flock, plus a flock class that represents a whole flock of these boids. A single boid will have to know at least 3 things for now: their position, where they are on the screen, their velocity, how fast and which direction they're moving in, and the maximum speed a Boyd can move. Now, in a large flock of these things, there's lots of mathematics involved. And so to make things much faster, we're going to use Apple's SIMD framework. This stands for Single Instruction, Multiple Data. Allows us to do mathematics on large amounts of doubles very, very quickly. Of our 3 Boyd properties, only the position should be passed in externally. So our flock can create Boyds where it wants them. We can give each Boyd a random velocity to begin with. They just float around by themselves. OK, time for some code. Lots of it, but don't worry. It'll be available to download at the end. You haven't got to take pictures or follow along unless you're feeling very brave. Here's our Boyd class. Like I said, position, velocity, maximum speed, all using the SIMD2 double, an X and Y position. Now, we're going to use lots of these SIMD2 doubles, lots of them. So to save some space on my slides, a type alias, just D2, an X and Y value holding doubles. So really, we have this. Position, D2. Velocity, D2. And then maximum speed of 5. Same thing, just shorter code to fit on slides. In the initializer, it'll pick a random direction between 0 and 2 pi radians. That's 6.282. And then that's our Boyd finished for now. That's enough for now. Very, very simple. As for our initial flock object, this is going to store the width and height, so it knows how much space our flock has on the screen. And also an array of the Boyds inside the flock. In the initializer, we'll stash the width and the height away for later on. And then loop 200 times to create 200 objects in our flock. Each time, make a new Boyd at a random position, random width and height, and add it to our array. So we now have a flock full of these objects ready to go. Now, in practice, this will work at any size, but I've chosen a size designed to fit my slides. In this case, over in Content View, I'm going to use 1280 by 720. That's my slide size here, using @state so it stays alive while our code's running. So now we have a single Boyd. We have a flock of Boyds. It's now time to draw them in SwiftUI somehow. So we'll make a timeline view using an animation frame rate so it draws regularly, and then a canvas, giving it the same width and height as our flock had. When it comes to drawing one Boyd, we'll load the SF symbol for a triangle and tell the context, prepare to draw this triangle, please. We can then loop over all our flock so we can position and draw every individual Boyd in our flock. Now here, I'm going to say, let's just draw our Boyds in green for now. It's a fixed color, but we'll change that later on. We can then get a copy of our graphics context, move its location to the Boyd's position, and then draw the Boyd. Now this part, getting a copy of the graphics context really matters. It allows us to make individual changes to the context before each Boyd is being drawn, so it won't affect how other Boyds are being drawn. And after all this code, we have that. Not very impressive, I know. Don't worry, it'll get better. I know, right? Wow, yeah. A whole bunch of small green triangles, which is rather dull. But it's a start. Boo-how. Watch it out. To make things slightly easier for you to see, we're going to scale up our Boyds. So 200% tall, and now it looks like that. So you can see a bunch of these triangles on the screen. That's our Boyds so far. They're all pointing in a particular direction. But it's the wrong direction. We gave each of our Boyds a velocity that describes how they're going to move on the screen. So we need to use that for their direction rather than always pointing up. If you remember back to school, we do this with atan2, with the velocity y and x. That gives us a radians direction. And you want to apply this to your context, but you want to do it after translation, but before scaling. The order matters. There are two important things to watch out for here. First, you want to add half of pi, so triangles point up when they're supposed to be pointing up. But second, you must do your translations in this order. Translate, then rotate, then scale. Otherwise, the result will be wrong. If you're not sure why, imagine drawing a grid like this. We have a 0, 0 at the center of our grid right now. If I translate this thing to 300, 100, it'll move to there. I can then rotate 45 degrees to get this, and then scale to 200% to get that. That's exactly correct. But if we do things in a different order, for example, we start 0, 0 again, and then rotate first, any movement we do will apply to that rotation. It'll go in the wrong direction. So do it in the correct order, which I've done here. So now all our arrows are, amazingly enough, pointing in the correct direction. Of course, the next step is to make the boids actually move somewhere, to do something interesting. Move the direction in which they are facing. And we're going to break down each of the three components of the Boyd's algorithm into its separate method here: cohesion, separation, and alignment. So in Swift code, it'll be three separate methods: separate, align, and cohere. These are all simple method stubs right now, all returning 0. They do nothing to impact our movement algorithm until we actually change them later on. Remember, D2, alias for just X and Y. That's what it's doing here. So we have these three: separate, align, and cohere. And we're going to wrap these up in one larger method, a single parent method that will call each of these three in turn and apply any weighting to them to make one be more valuable than others. We might say, for example, that separation matters more than aligning and cohering. So we have a fourth method to wrap the other three, call the other three in order. So now we can actually add some code to do some real work. This is another method on our Boyds. And it's going to update any particular Boyd inside the flock. And this is going to call that movement in method to figure out the Boyd's new velocity, adding that to whatever is the current Boyd velocity. So the objects adjust slowly rather than just jumping around to their new value. Critically, this will also limit the velocity to the maximum speed Boyds can move, using that maximum speed constant we made earlier. Again, a bit more mathematics for you. You look smart. To limit the vector requires just 4 steps. You want to try and first calculate the length of the vector. If that's less than our limit, we're done. Send it back. Otherwise, divide that by our length and then multiply that into our vector. We can make that a simple extension like this, thanks to SimD2 doing all the work for us. So once we know the Boyd's velocity and we limit to our maximum speed, we then add that to our position so it moves on the screen. And this is how it looks in code. Get the movement, limit it, add it to our position. So at this point, every Boyd has just enough logic to know how to move. Although in practice, everything returns 0. It's still a good foundation for us to build on. We have so far our current time live view code is just enough for us to move on to code to make the whole flock move. We already have this code here. We're going to use that to call a new method in our flock to make it move, this one here. We loop over our array and say, please run. It receives a date from SwiftUI, but ignores the date from SwiftUI. If we don't accept it, SwiftUI assumes we don't need it and will stop redrawing. We must at least accept it. And now to bring all together, we just say update in our timeline view. And all this work lets each Boyd update itself as the display is redrawn, which is 60 or 120 times every second. If you run the code now, here's how it looks. It's better, but it has some problems. First, there is no flocking. Every boy just moves straight ahead. And second, they've all gone. All the boys move off the edge of the screen and don't come back. Now, the first behavior, no flocking, happens because all our code is saying 0, 0, 0. There's no flocking code in there yet. That's fine. We'll fix that shortly. The second problem is easily fixed. I want the boys to wrap around the screen edge. So if they move off the left edge of the screen, they should reappear on the right edge. Or go off the top edge. They should reappear on the bottom edge. Just wrap again and again and again. To make that happen, we have a new wrap-in method that checks whether the boyd's off screen. If so, wraps around the edge. And there's no magic here, just a bunch of conditions. Are we off the left edge? Go to the right edge. Are we off the right edge? Go to the left edge. Again and again. Simple conditions here. So the boyd will wrap itself automatically when we call wrap in our flock. Small change, but it now means our boyds still have no flocking behavior, but at least they don't disappear. They'll stay there for the entire time now. So now we have good movement in place. We can start to build in Reynolds-Boyd's algorithms. There are 3 of these, remember. Cohesion, separation, and alignment. And they're being run individually, so you can add weights to them to make one worth more or less to adjust the way your flock behaves depending on the results you want to have. To start with, we're going to change the movement in method, this one here. So we call separate from and give it a weight of 2. This number, 2, is entirely arbitrary. It's my choice. But I found it means boyds work well. They want to get close, but not too close. This will make more sense later once we have other behaviors factored in. Next, we have to add 2 helper methods here in the boyd class. One that will find all the neighboring boyds within a certain distance, and another to make sure we smooth out movement as we're going. So it only has a small impact on the overall movement. First, finding neighbors. This matters a lot. Because the whole point of flocking is that each boyd adjusts its movement and speed based on other boyds around it. How far they look for neighbors will vary across the 3 behaviors, but they still have to figure out which other boyds are within some cutoff distance. And there are 2 small complications here. The first of which is, as well as finding all the neighbors, we also want to know how far away those neighbors are. This is because having that extra piece of data allows us to weight adjustments so that neighbors who are further away have less of an impact on each boyd. The second complication is that calculating distance from one boyd to another is done using Pythagoras' theorem. Except now we have a quadratic runtime. Not only are we looping through every single boyd in our flock, but every boyd must loop through every other boyd in the flock to find out how far away it is. Now, we can't avoid that performance hit. The n squared is required here. But we can make it run faster. Again, back to high school or middle school mathematics. Pythagoras' theorem, a squared plus b squared is c squared. In our case, that means a squared would be the horizontal distance between 2 boyds. B squared, vertical distance between 2 boyds. And so c squared becomes actual distance between 2 boyds. And these calculations are very, very fast. But the next part isn't. To get the actual distance, we have to square root c. And that's slow. It's very, very slow. So we're going to adjust our code a little bit to not square root stuff. We'll just square our cutoff distances to get the same result, just much, much faster. So we'll make a function called nearby. Tell me which boids are nearby. It'll accept the flock and a cutoff distance to check. How far to look for nearby boids. We'll then make it send back an array of all the nearby boids that were found, along with their distances. And then inside there, we'll go over the entire boids array using compact map. We'll send back a boid and its distance if it's within the cutoff. Otherwise, nil, it's ignored. Helpfully, the SIMD framework has a built-in function for calculating these square distances. So we'll use it here. And that is all our code. That's our first helper method written. The second one is to simplify and smooth movements gently. I'm calling that one steering. Convert a movement amount into a smaller adjustment for a boid. So we smooth out changes so they look natural. This requires several steps. First, we normalize the change. This means giving it a length of 1, no matter its direction. We then multiply that by our maximum speed. This means our movement will now have a length of maximum speed in the same direction it originally had. We can then subtract our current velocity here, so we make gradual adjustments rather than jumping around, small changes. And then we'll limit that to the largest possible value you want boids to move at, which limits how fast they can move and change direction. Again, 0.1 is an arbitrary number, but I found it works well. We can then send it back. So those are our two helper methods to make our life much, much easier. So now we can add some intelligence here, the separate from method. Right now, it returns 0 always, do nothing. Make it better, we're going to start by finding all the boids who are within 900 squared points of us. So that's 30 points nearby. If there are none, exit immediately. Send back 0, do nothing. If there are some, we want to figure out the average. So we're going to calculate the average of all our position differences, which means reducing all our boids to a total, then dividing by the count and sending it back, the mean average. Inside there, we want to have the weighting. We want to weight adjustments based on distance, so that neighbors who are further away have less of an impact. And that's this part of the code here. After all, it's much more important to stay away from boids that are right next to you than boids that are at the far edge of the cutoff. That's our new method, and now we have something actually interesting. The boids will move around, but never collide. They want to stay away from each other. A bit like little fish in a pond, for example, swimming about, but staying away from the rest of their flock. So that's cohesion. But at this point, we've done almost all the hard work. And we're now just one function away from getting quite remarkable results. First, here's our current movement in function. We're going to add in the results of both align and cohere here. Just slotting them in. There's no weighting here, which means our boids will prioritize separating over aligning and cohering. And remember, both these functions still return 0 for their values. Adding to the equation will do nothing at all. It'll behave the same. We can now go ahead and fill in the align function. So it finds all neighbors with a distance. I've chosen 2,500 squared points here. This time, we want to read out just the speeds they're going at, and again, average them, which means adding them all together, and then dividing by how many there were, the average. And then send it back through our steer helper function. And now, when we run the code again, you'll see our boids start to find each other and will swarm across the screen. If you leave it running long enough, they'll form one huge swarm, all moving in roughly the same direction the entire time, give or take minor course adjustments. So it's pretty close. But it's not really how flocks behave. Unless they're going somewhere special, they prefer to kind of swirl around, making clumps, then spacing around, then making different clumps. This is where the final part of Reynolds' algorithm comes into play. We need to fill in the cohere method that encourages boids to make clumps with their neighbors. This thing is almost the same as alignment, except for two small things. Firstly, we want to average positions rather than velocities. And then we want to make the change smooth, which means subtracting our current position from the average of our neighbors. Otherwise, we'll jump to the average rather than moving towards it. So again, very similar. Find all our nearby boids. If there are none, exit straight away. This time, read out their positions. Again, add them up and divide them. Get the average. But then subtract our position, so we get the average distance from this boid to the rest of the flock. And then send it back through our steering code to smooth out the movement even further. And with that in place, things look even better. Miniature swarms will now form by themselves as the boids clump together and depart again. If you leave it long enough, they have mini swarms become big swarms, and then mini swarms again, regularly happening like birds would do. Now, we could leave it here, but I have like 11 minutes left. We can do better. I want to add two small but important changes to our code that will really bring it to life. First, we're going to add teams. So we have multiple flocks of boids on the screen. And also, we're going to add object avoidance. So our boids will try and stay away from a particular point on the screen. Let's start with teams. We can give each boid a random team color. One of these four: green, white, pink, or yellow. A single property in the boid class. Now, using this property will be optional, so you can see with and without team behavior. So we'll say there's a Boolean in our flock class called team mode to track if teams are enabled or not. When it comes to drawing the boids, before it was always green, but now we'll say if we're in team mode, use the boid's own color. Otherwise, do it in green. And then we'll add a tap gesture to the whole timeline view to toggle team mode. Now, to make it actually do something, we need to adjust this nearby function, which currently looks like this. Loop over all the boids. At the very start of the compact map call, we're going to ignore any boids that don't belong to our current team, but only when team mode is enabled. And that's it. Now our flock starts by default in one big group, but if you tap the screen, it should switch to team mode, where they'll form a little white flock, a little yellow flock, a little pink flock, and so forth, individually flocking amongst themselves. As for avoiding obstacles, this takes several steps to be really interesting. First, store a property that stores where the obstacle currently is. So we want to add this to our flock. Where is the obstacle the flock should avoid? By default, I'll make it the middle of the width and the height, so the middle of the screen. Then in SwiftUI, we'll add a drag gesture, so you can move your finger around the screen to move the obstacle around. And that completes all the code to place and move an obstacle. But the boids don't yet know how to avoid it. To make that happen, we need to have another new function here, similar to our three previous behaviors, so it returns 0 for the time being. We can then factor that into our movement method by putting this before the return statement. I've given this thing a weight of 20. Boids will very strongly prefer to avoid going near the obstacle. They'd avoid it at all costs. So now we're going to fill in the avoid method. This takes 4 steps. First, figure out how far away we are from the obstacle. If we're too far away, return 0. The boid will not care if the obstacle is very far away. Otherwise, we subtract the obstacle's position from our position and divide that by a distance to the obstacle so we care more about it when it's close to us. And finally, put that back through our steer smoothing function and send it back. And that's it. You can now drag with your cursor or your finger or your hand to break up this whole flock with your mouse. All the boys respond immediately by fleeing away from it. And honestly, it's kind of fun, making them run away from your finger. And this is just the beginning. If you want to go further and further, you could add multiple obstacles for your boys to fly around and move around or whatever. You go into 3D space, so you could make their hands wave around, make the boys fly around or next to the hand or away from the hand. Or add predator boys, so boys will avoid those things, avoid being eaten, whatever you want to, or add other logic. There's so much more you can do with this simple behavior. The point is, what we've done is we've started small, trivial code, and made it better and better and better. You know, our first version was some boids that just stood there, little triangles on the screen, nothing. Then we made boids that move and wrap around the screen. And we made boids that from the Craig Reynolds algorithm that will separate from the rest of the flock, that try and stay close to other boids. Then we had boids that have mini flocks based on who's nearby. Then we added team support to them. Then we made them avoid a place of our choosing. We got better and better and better through iteration. Each part of that logic is trivial. Each individual boid finds other boids that are nearby, then averages what they're doing to adjust their own movement. But this kind of thing put together results in something very close to the real thing. They flock around and fly around, forming things like real flocks do. I think this is a great example of AI at its best. It's easy to understand the logic here. It's extremely fast, even on very old hardware, yet somehow creates something beautiful. Thank you very much.
好的，好的，那非常感谢 Paul 的精彩演讲啊。然后现在是我们的 Q&A 环节，有没有人想问 Paul 一个问题？时间有限，我们就有一个机会啊。
Hey, Paul, that was fascinating. I'm curious, something like flocking, do you think that could integrate with particle systems like Vortex? Could you integrate the two together?
So for folks who don't know, I last year released, or year before, I've lost track now, an open source library called Vortex, which is a particle effect system for SwiftUI. And it's very, very cool. Lets you make fire effects or snow or rain or you name it in SwiftUI. Vortex already has object avoidance built into it. If you try a sandbox, the spark effect, you can make the fire run away from your fingers, which is quite fun.
So it's the same as what you just shared of the object avoidance.
No, flocking's smarter again, because they don't rely on your finger necessarily, they rely on themselves to align and cohere amongst themselves. But it'd be great fun, right? It's almost like magical smoke has its own idea of movement.
It combines or everything.
Yeah, yeah. I suspect the problem there becomes, even with SIMD2, it'd be quite slow to upload 1,000 or 2,000 of these things. You'd want to probably switch to Metal, maybe, to get really, really fast GPU transformations. But it'd be a good idea. It's open source, you know?
Oh, I could do it. I got the code.
I'm waiting for your PR, you know?
Awesome. Thank you so much, Paul.
No worries.
好的，那非常感谢大家，因为时间关系，然后希望大家如果想跟 Paul 继续交流的话，可以在接下来然后继续交流。Yeah, yeah. So thank you, Paul, for sharing.
Okay.
Yeah, 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 yeah.
Okay.
And people can cheer for Paul again. Yeah.